Section 10.6 Gas Mixtures and Partial Pressures. Thus far we've considered mainly the behavior of pure gases, those that consist of only one substance in a gaseous state. How do we deal with gases composed of a mixture of two or more substances? While studying the properties of air, John Dalton made an important observation. The total pressure of a mixture of gases equals the sum of the pressures that each would exert if it were present alone. The pressure exerted by a particular component of a mixture of gas is called the partial pressure of that gas. Dalton's observation is known as Dalton's law of partial pressures. So if we let P1 be the total pressure of a mixture of gas of P1, P2, and P3, and so forth, to be the partial pressures of individual gases, we can write Dalton's law as follows. Pressure total equals pressure 1, pressure 2, pressure 3 sum. This equation implies that each gas in the mixture behaves independently of the others, as we see by the following analysis. Let N1, N2, N3, so forth be the number of moles of each of the gases in a mixture, and N sub T the total number of moles of gas. If each of the gases obeys the ideal gas equation, we can write P1 equals N1 over RT over V, P2 equals N2 over RT over V, and so forth. All the gases in a mixture are at the same temperature and occupy the same volume. Therefore, by substituting into equation 1012, we obtain N to the T times RT over V. That is, at constant temperature and constant pressure, the total pressure is determined by the total number of moles of gas present, whether the total mole represents just one substance or a mixture. Partial pressures and mole fractions. Because each gas in a mixture behaves independently, we can relate the amount of a given gas in a mixture to its partial pressure. For an ideal gas, P equals nRT over V, and so we can write pressure 1 over pressure total equals N1 over N total. The ratio N1 over N total is called the mole fraction of gas 1, which we denote as X capital sub 1. The mole fraction X is the dimensionless number that expresses the ratio of the number of moles of one component to the total numbers of moles in the mixture. We can rearrange equation 1014 to give pressure at 1 is the total pressure times the mole fraction of 1. Thus, the partial pressure of a gas in a mixture is its mole fraction times the total pressure. The mole fraction of nitrogen in air is 0.78. That is, 78% of molecules in the air are nitrogen. If the total barometric pressure is 760 torr, then the partial pressure of nitrogen is 0.78 times 760 is 590. This result makes intuitive sense because nitrogen makes up 70% of a mixture. It contributes 78% of the total pressure. Collecting gases over water. An experiment that's often encountered in general chemistry laboratories involves determining the number of moles of gas collected from a chemical reaction. Sometimes this gas is collected over water. For example, solid potassium chlorate can be decomposed by heating it in a test tube in an arrangement such as shown in Figure 1016. The balanced equation for the reaction is 2 moles of potassium chlorate breaks down into 2 moles of potassium chloride plus 3 moles of oxygen gas. The oxygen gas is collected in a bottle that's initially filled with water and then inverted in a water pan. The volume of gas collected is measured by raising or lowering the bottle as necessary until the water level inside and outside the bottles are the same. When this condition is met, the pressure inside the bottle is equal to the atmospheric pressure outside. The total pressure inside is the sum of the pressure of the gas collected and the pressure of the water vapor in equilibrium with liquid water. Pressure total is the pressure of gas plus the pressure of the water. The pressure exerted by water vapor at various temperatures are listed in Appendix B.